Yeah, thank you everybody for joining us for the great session today. My name is Ahmad Fatahi. Thanks to Kevin's introduction, you already know what basically we are up to and what we do here at TIBCO. I'm a director of data science. I'm being joined today by my two colleagues, Marcelo Gallardo, who's a senior solution architect here in the office of the CTO at TIBCO, and Atir Alatar, who's a lead data scientist at TIBCO on the chief analytics side. Here's a standard disclaimer and confidentiality for the session. And so the agenda today, what we're going to cover, I'm going to start with introducing what TIBCO does, who we are and what we are, what our purpose in life is, basically, as a company. And then we quickly pivot into the actual problem that we're going to talk about today that's related to your interest, the IoT community. And then going deeper into the various pieces and components of this problem that we are going to tackle. Data gathering at the edge. It's a true IoT case that we're going to cover, followed by analytics, building a machine learning model, and all the way to deployment, right where the data is at the edge. And then we'll close with some Q&A. And as a quick reminder, we are going to have not only a Q&A, but also I'm going to post our 3 contact emails. So in case something comes up later, you can reach out to us, or through the IoT community is fine as well. So let's get started. Who's TIBCO? We are all about making intelligence bring value to businesses, the whole spectrum of that, and we're gonna see a little bit more about that. So connecting the intelligence from the raw data, in this case close to the edge. In some other cases, it can come from various places. As we'll see, we're present in various different verticals, so the nature of the data can be very different. So we start there, and then going through the unification of the data to basically make sense of each data set or data stream in the context, which takes a lot of unification management of the data, and then all the way to the analytics, which we call predict, and to basically help make better sense of these 3 pillars that we tackle. We like to talk about these 3 main columns or pillars of what we do. And actually today we are going to cover quite a bit of mainly the first column, connect. We are going to see how we connect to a source of data really close to the edge, and all the way to mainly the right side. The predict side, given the fairly limited scope of this problem that we're going to see today, there's not much unify in this presentation, but the breadth of the products cover quite a bit of that. And to dig a little bit deeper into each vertical, the connect can cover not only data addressed and batch type of data connection, but also streaming and events. The other aspect is on the unify side, we have things like master data management, or products for master data management, for very importantly, virtualization of the data. So your whole organization, if you belong to an enterprise or a pretty wide or disparate environment, data virtualization is really critical to make your whole data available and trustworthy for the rest of your organization. And last but not least is the analytics side, which we call predict, and that is the part that we do machine learning, not only just the modeling, but also connecting, integrating with the sources of the data, the exploratory phase, the visual part, all the way to deployment, and which requires streaming and inference in real time. Speaking of the various places that we are present already, we are not a startup. We have been around, and we have been already present in many types of small and large organizations, including 21 out of the 25 global 2000 companies. And as you see, several different verticals from manufacturing to healthcare to retail and so forth. What we are seeing today is going to be most likely closer to manufacturing use cases, or you can argue retail might be a good use case, which is related to sound in the environment and making inferences based of that. And transportation might have some good use cases for that. We actually had a recent customer who wanted to do a similar thing in the healthcare vertical. So while the story today is very specific, the same principle can be applied to several verticals. For those of us who are more on the architecture side and more technical, this is a logical view of the breadth of our view of how a connected intelligence environment actually is built. So on the left-hand side, you see where data happens, and we just talked about the data at rest and databases that we can connect to, as well as streaming, and we have connectors for pretty much all of the popular sources in the world. Moving to the right, we have for the unification of the data, we have all of these master data management products, technologies to make several data sets available and standardized and cataloged and virtualized without moving large amounts of data, and make them available to the rest of the organization. And moving all the way to the right-hand side is where the actual usage and the service of the data happens. It can be pure visualization for business intelligence purposes, or it can be more sophisticated modeling and AI operations that happens in many organizations. Moving to the next step of sophistication, we have the analyze part in the middle. Obviously, when the models are built, you want to apply that in real time to your data. And to make that happen, we enable the data scientists and the management of the models in production, who can that can operate not only on data at rest and batch data modes, but also in real time operate on inference. And actually, we are going to see both of these examples today, where we build a model on a batch data set, deploy it, and then have it run on incoming data in motion. And to make that happen on the process, more on the process side, we have technologies and products that covers master data management on the data unification side, and the API management on the usage side for not only management, but also security, which is a huge topic of importance these days. And to overlay that with what TIBCO does basically with its products, this is the labels of the boxes change to basically our products here, where you can map those functional boxes to TIBCO products for your reference. And today we are going to basically cover pretty much these green arrows. The top branch is where the streaming happens post deployment of the model, and the bottom branch is what we actually cover first for the training of the model and deployment. And so in organizations of today, we all know that data science and analytics operating on data is a team sport. This is a view of which personas are covered through our products, and which products serve them. And you can see this is not a niche product. The breadth of the products is actually pretty wide, covering the visual part on the top in our TIBCO Spotfire product, that actually we are going to see some of the results in there, which can help you not only in the exploratory phase, but also the results of the model can be served there, as commonly actually that's the case. The we support the typical notebooks for data scientists. For the management of the processes, we have a drag and drop simple no code tool called Team Studio that helps data scientists to actually build those processes, bring in data, connect to the data source, filter it, do feature engineering, and build a model, compare models, and then have it deployed. We're going to see actually some elements of that today. And for the machine learning engineers, we have model ops to actually deploy them and monitor them for drift and everything that happens post deployment. All right, so now that we have a high-level idea of what TIBCO does and the breadth of the products, let's start talking about the specific problem that we're going to talk about today. And it's actually a very familiar one. So imagine that you have an asset in the field. Actually, it's pretty generic. It doesn't have to be anything in particular. And in order to maintain it, the traditional ways are either you maintain them on schedule. Actually, many traditional cars, automobiles are like that. Every 5,000 miles or 10,000 kilometers, you just, regardless of the condition of the car, you just take them in. Which is basically those planned costs. You take it in on clock and maintain them. And as you can see on the bottom right curve here, the green curve basically reflects that cost. The shorter the period, the frequent, the interval of your maintenance, the higher the cost, because you just do more maintenance. On the other end of the spectrum, you can just not care and wait until the equipment fails, which is the pink or salmon curve here. And the longer you wait, obviously you're rolling the dice and the cost goes up. The sum of these two costs represented your total cost. And if you basically don't pay attention to the condition of your maintenance, you want to minimize the sum, and you can optimize the maintenance interval based on that. What we're talking about today is improving on that. So if you take what I just set up as our benchmark, we are going to show a process where we take into account the condition of the actual asset, in this case a fan, and build a model and leverage the sound that fan makes in order to look at the condition of the fan and also be able to predict if it's due for maintenance based on its condition, not just because of time. And it's actually shouldn't be too unfamiliar because of experience I'm sure a lot of us have had with a relative or someone in our circle of friends who are experienced enough human beings to just listen to the sound that the car engine makes, and they can tell you that, yeah, something is off, something is anomalous here, it doesn't sound right, quote unquote right. And what we are showing today is exactly what we're building, is exactly that. It doesn't sound right kind of model to train models to pick out those anomalous behaviors. And these are some motivating numbers based on the analyst reports, how much productivity, like 25% productivity based on Deloitte, can be gained by doing predictive maintenance as opposed to either clocked maintenance or wait until it fails regimen. And you can avoid 70% up to 70% of the breakdowns, and the maintenance cost on average can be reduced by 25%, which shouldn't be a surprise. Certain industries are extremely sensitive to unplanned failures for various reasons. They do everything they can. They can sometimes go way too conservative to just bring down an asset and maintain it before it fails, because if it does unplanned, it can cost a lot of money. And this session in particular, the story we're going to hear is going to be applicable to, in a large part, these three personas. Let me actually start from the right, the closest to the field, the actual technician who works on the assets. They can have a much more efficient day at work, because they can optimize which equipment, which fans to target for the day, and have a good view of how many assets are in dire need of maintenance. And if not, they can find something better and more valuable for the organization to do. And as a result, they can, speaking of the human aspects of it, they can have a better job satisfaction, because they know they're working on something that matters on that day. And moving up the management chain in the company, the factory managers are very interested in this, because it just helps them run a more efficient team and happier. And the last but not least, the executives, they can, as a whole, save a lot of money by not only running a more efficient operation because of everything we just mentioned, but also they can keep their assets actually running for longer, because they maintain them when they need maintenance. So the lifespan of their fans in this case actually increases as well. And the process works like this. So there's sensors, in this case a microphone that collects the sound signal from the fan on the left hand side. It's passed on to a machine learning model, which is trained to pick out the normal signal and the anomalous signal, and it's deployed close to the edge. And then the model, when it's deployed, it predicts in real time if a sound sound signal looks anomalous, or I should say sound anomalous, and it basically needs attention. The logical architecture that we're going to see is like this. This is logical. The actual flow of the data is a little bit more sophisticated. We go back and forth in some cases, but there's a data tier on the bottom where the actual equipment sits with the sensor, and Marcelo is going to actually leverage a Raspberry Pi as the engine, compute and storage engine close to the edge, and pass it onto a database, which is then picked up by the analytics side for the model building. Speaking of the middle tier, the left box in the middle tier, TIBCO Project Air, that's actually the engine that it's a project that we've co-built with some of our large customers to enable these AI applications. It's going to play a significant role in the technical story that we're going to see here. And then when the model is built, in the middle layer, we're actually going to see some TIBCO Spotfire. I'm talking about the right box in the middle tier. For the visual side of it, the resulting model is ready for the consumption tier on the top, which is going to be deployed again close to the edge, and it can be pretty tiny or larger. It's actually Project Air doesn't care. It applies to all sorts of hardwares and environments. And in this case, the consumption layer is that we're going to see is more on the like a user app that we're going to see in Spotfire, but it's agnostic. Everything I just talked about our products and technologies are agnostic to many different environments. It can be consumed as a notification source for whatever notification engine you use, or a website, a dashboard, whatever it is. So that's the high-level architecture. Without further ado, I pass it over to Marcelo, who will basically start to dive deeper into the actual implementation. Marcelo?
Yes, can you show the slide, please? The first slide. Hello, everybody. My name is Marcelo Gallardo, and I am a member of the TIBCO Labs team. In this section, I will give a very quick overview of what Project Air is and show some of its capabilities. So what is Project Air? It is an open source initiative from the TIBCO Labs program. It aims to bring intelligent insight from the device to the boardroom. This is accomplished by allowing users to easily connect and interact with any kind of IoT devices, process the device data at the edge or at the cloud or wherever is needed. Also being able to run on any edge device or any cloud provider. Also, we allow to store and analyze data as needed and allow it to easily extend every layer of the architecture for easy integration with other platforms. Next slide, please. So in summary, Project Air provides capabilities for connecting to devices and processing its data, managing the data from the devices, creating triggers and flows to respond to IoT events, store the data in long-term big data repositories for historical analysis and analytics, and also the visualization of the IoT data. Also, we provide a customizable UI to monitor, measure, and react to these IoT events, and combining the IoT data with the ML models. So how is this accomplished? Can you go to next slide? This is a very high level architecture view of the Project Air. We have components that are deployed at the edge, as well as some components that can be deployed at the cloud or on premise. So going from left to right, we can see on the left, we have the IoT devices producing the events. And then we have an IoT gateway that usually is at the edge, where we deploy the Linux Foundation's project, the HX Foundry project, where we build on top of that. The project is built on top of that framework, and we provide the edge components to interact directly with the data that's coming from HX. And then on the right-hand side, the Project Air provides some components to interact with the components at the edge, where we allow easy integration with the enterprise applications like your visualization analytics tools like Spotfire, the data science tools, and any other application. So with that said, I will start going to share my screen and give a quick overview of the project, a live demo. And actually, I will start showing you. Let me share my screen first. Right, here it is. So when you open a Project Air, as I mentioned, we provide a user interface that allows the easy interaction with the devices. So when you get started, you get a top-level dashboard of all the devices you are managing. In this case, I have two groups of devices. One is running on my Mac laptop, and another group of devices that I have devices connected to this Raspberry Pi. The Project Air allows you to manage the devices very easily. Once that the devices are configured, they automatically are available at the dashboard, and then you can start working with the devices. So for example, on my devices that I have running on my Mac, if I click here on the view details, I can see all the devices that are available on this machine. So in this case, I have two simulation devices. One's called REST device and another MQTT device. And here at the top level, it gives me an overview of some metadata from the device. And at the top, we can see all the different sensors that this device has available. So if I start clicking on the device, for example, this is a sensor that is emitting integer 16 type of data. So here we can see the different metadata for that device. And at the bottom, actually, you can see a chart that will display the data that sensor has emitted. In this case, I am not showing anything because I haven't configured any process to handle the data coming from this sensor. In the next section, I will show you how to do that. So again, you can jump between the different devices and explore the different readings or different data from the devices. Going back to the main dashboard, we also provide a capability to create business logic data flows with using the data coming from those devices and be able to deploy those data flows either to the edge close to the devices, or if the requirement is you can also deploy it to the cloud or wherever you need it. So to start creating the data flows that we call pipelines, first thing you have to configure some endpoints where you will define some of the information that is common for the data flows. So in this case, we have three things that you need to pre-configure. Like the first thing is the protocols, that is like the messaging information that you will be using your data flows to receive the data or where you want to send your data. So here, for example, here I define an HMQTT connection to, this is a connection to the transport to the channel that HX is sending all the events. So we will be receiving the events from all the devices connected to HX through this channel. And then I have also defined Air MQTT, that's MQTT broker that is running on the cloud, that where Project Air is subscribing to receive the events and be able to display in the dashboard that we are looking at. Okay, we have also defined some data. Oh, before I go there, we support many, right now we support 3 protocols. We support MQTT, we also support Kafka and AMQP, and a few more are coming on the works. For data stores, I have defined a data source for a Postgres database. That's where we will be using actually for this demo to capture all the events that are coming from the fan and store there so that the data science team can analyze that data and create the data model. So when I click on the data store that we created, you can see the connection parameters to that database. And that's, again, in this case, it's Postgres, but we support many other data stores like Snowflake, Oracle, MySQL, and a few more. Same thing with the models. The user interface provides a screen that allows you to bring models that we provide tools to containerize and then deploy them also to any machine on the network that we are managing. So here on the models screen, here we allow you to configure the model and specify how to reach to that model, how to connect to the model. So in this case, I have 2 models, and they are the same model. One is running on my Raspberry Pi. So here's how I connect to the Raspberry Pi service that this model is enclosed. And here also I can provide how I want to send the data to the model. So in this case, the pipeline, the data flow is receiving data from the devices, and the data itself is in a structure, and the data for the sound is in a value field. So here's the way we specify that. So we are saying pick the data that the model needs from the value field on the data structure. And that's all we need to do. So the model is configured. Same thing for the other model, which is the same, but it's deployed on a different machine. So the only thing that changes is the IP address. So we will select, when we are configuring the data flow, we will select what model we want to use. Again, this can be a model that is also deployed on the cloud. It depends the requirements. If you need to have like real-time response for the model, then you are more likely to deploy the model close to the device. If your requirement is that it doesn't need to take like milliseconds to respond, but then you might be able to deploy models on the cloud or wherever you need it. Okay, so let's go back to our dashboard, and now we will work on the first scenario. We are going to create a data flow that will help us collect the data coming from this fan and store it in a data store. So to do that, I am going to work on my Raspberry Pi configuration on the machine that is close to the fan, that is managing the fan. So in this case, I go to click the pipeline icon here, and this will take us to an editor where you can create the business logic using the data that's coming from the devices. So at the top is this editor is empty. And when you right click, you are presented with a series of activities that you can use to create your data logic. Again, these activities are created by are provided by the project, but we provide an SDK so that if there's some activity that is not available and you need for your business logic, you can easily add to this set of activities. So we'll start with a data subscriber. We select the data subscriber, and then we select where we want to subscribe, where we want to receive the data. In this case, we want to receive the data from the edge channel. So in this case, we select the edge MQTT. That's where the data is coming from the device. That's where it is in the format that we understand. So what we want to do with this, in this case, the only thing we want to do is just the data extraction and storage in some repository so that the data science team can analyze the data. So in this case, we are going to use a data store activity and select where we want. In this case, we select, we want to the Postgres database. That's where we want to store the data. And with that done, we can connect the two activities, and that's it. And then we can give it a name to this data flow. We call it store data. And here on the type, you can select where you want to deploy this process. So we are going to select edge because we want to deploy this process close to the device. And then here we have two deployers that are available. One is the Open Horizon, also provided by the Linux Foundation, and another one is the one that we created for Project Air. And we will use that for this demonstration, and that's it. With that done, I click the pipeline, and you guys can see here that my pipeline has been saved. And at this time, I am able to deploy it. And if I deploy, it will start getting the data that is being emitted by my device that I have on the Raspberry Pi. It will collect the data and store it into a data store. For this part of the demo, I won't deploy it. I will do a deployment in the next section. Also, one more thing that you can see here is that I have another flow already created here. And as I mentioned, you can easily jump back and forth between different flows, edit and deploy it or whatever is required, or come back to your previous flow and make changes. So that concludes the first part of my demonstration, and I will pass back to Ahmad.
Actually, I think it's your section, right?
Yes, yeah. Let me share my screen.
So we are basically in the storyline. We are now moving to the analytics and the data science side that Athir is going to cover.
Can you see my screen?
Yes.
Okay. Hello, everyone. My name is Athir Alatar. I'm a data scientist in the analytics team. So I will talk about the part when Marcelo finished acquiring the data from the device and then storing it into whether it's like a cloud or like on the edge device. The step after that, we will access these sound files or like .wav files, and then we will start a couple of steps to transform the data into a numeric format in order to make it easy to be processed in the machine learning, like in our machine learning algorithms and routines. So basically, first of all, we convert all these .wav files into values arrays, and then we perform a short Fourier transform to convert all of these files into one data frame. And then let me talk about the TIBCO data science, which we use to perform all of these steps, basically starting from accessing the data, ending with exporting the model. So TIBCO data science is a team studio is an end-to-end data transformation and cleansing and modeling format. It's a collaborative environment, so there are so you can like work in teams, and then basically you can track all the activities of your team members, and then it's like a workspace environment. You can create your workspace, invite people to it, make it private, and then you can also like interact with other workspaces. It's also a low-code to no-code environment. So basically, all the functions that you need to perform, the most likely available here in a form of an operator, and then you just need to perform like few configurations, and then you have it up and running. It also leverages your local resources. So, for example, if you have, talking about the big data, if you have a Spark server in place, or like if you have a Hadoop server, Team Studio can hook up to these resources and perform the distributed calculations, or like on memory, like in memory calculations using these resources. And then it's not also limited to like these resources. You can almost connect to everything you can think of data sources. You can connect to S3, Redshift, Cloudera, you name it. I mean, there are like lots of data sources you can connect to, plus the static files. One of the also the features in Team Studio is you have version control, so you can track like all the changes that you or like one of the team members did to the modeling, and then you can like bring back any previous copy, so nothing is lost. So that's like kind of a simplified copy of a model ops here in place. So, for example, if we want to bring a previous copy, we can just like select it, replace the current, and we still have like the other option. One last thing is TIBCO Data Science has a feature called Touchpoint. So what the touchpoint is, if you have, for example, a model, if you develop the model, and then you want to provide the end user, or like for example, someone in a non-technical team. You don't want them to go through like nitty-gritty details of the workflow. You can provide them with a simple interface. They can just input like a few parameters that you need to run your model, and they can run it and get the results without getting into the complications or like the details of the model that they don't need to. So that's also another feature of let's say non-technical people. They can interact with the model. Back to our modeling process. So after we perform the transformation, which is like in this step, and basically we just use Python notebook to perform all of this. We tested 3 models. We tested isolation forest, autoencoder, and then local outlier factor. We just like deployed them in Python notebooks, and then we looked at the accuracy. It turns out the highest accuracy was coming from the isolation forest. We achieved 92%. So we went with the isolation forest, and then we exported the model into a pickle file, which is like a single file. It can be deployed. And then we handled the model back to Marcelo's team to be deployed and containerized on the edge. And yeah, this is kind of like a description for the models that we use. So we went with the isolation forest. One of the features of the isolation forest is if there is an outlier, like there's a point which is an outlier, it's very easy that this point will be isolated at the beginning of the algorithm sorting. So to this point, we acquired data from Marcelo storage, and then we converted that to like numeric format. We performed some Fourier transform, and then we started our machine learning approaches. We selected the high performing model, and then we packaged or like pickled the file into one, pickled the model into one file, and we handed back to the edge team to be containerized and deployed. So this concludes this part of my work, and then we'll hand it back to Marcelo.
Thank you, Athir.
Mm-hmm.
Let me share my screen again. So as I think mentioned, so the first phase of our project using Project Air was to just collect the data coming from the devices and store into a database so that the model can be generated. So once that the model is generated, as I mentioned, we provide some tools to containerize the model and actually put an envelope around the model and provide a REST interface so that we can call it from our data pipelines, from our data flows. I am not going to deploy the model as it is already deployed and is running, but just to give you a flavor of how to do that, we provide an infrastructure deployer here. And here's the registration. So here you will register the model. So pretty much it's just uploading Docker Compose file and some description of what the model does. And once that we register the model, then you can come to this other screen where you will actually deploy the model, where here you will select the deployer type, the location where you want to deploy and things like that. So that's just to give you a quick overview. Going back to our main dashboard, in this step, what we want to do is go back to the pipeline editor. And now that the model has been created and has been deployed, we want to start using it. So what we want to do is create a new pipeline that will subscribe to the events that are coming from the device, in this case, the fan. Once that we subscribe to we select again the channel where the events are going to be coming. And once that is done, the next activity we want to put in place is an inferencing activity. On the inferencing activity, you're presented with a selection of all the different models that have been deployed on this available to this machine, to this gateway. And again, as I mentioned, the models can be running close to the device, or it can be on the cloud or anywhere. So in this case, I have registered two models, as I mentioned, one that is actually running on a Raspberry Pi and another model that's running on my Mac. So I will select the model that's running on the Raspberry Pi. And when I select, it gives me like an overview of what the model does. So in this model detects anomalies from some samples that is coming from the fan. And at the bottom, you can see that this device, this gateway is managing two devices. There's the fan and another REST device. So here I want to select what the data from what the device I want to use. So if I expand the fan, I can see that this device has one sensor or one artifact that is emitting the data. So it's the microphone. So I select the microphone, and that's it. That's all I need to do for the configuration of my inferencing activity. So now I can connect the two activities. So I receive the data, run through the model, and then this is producing some results. So what I want to do with the results, I could send to my visualization tool in Project Air, which I showed you before. It provides different visualizations for the data. Or in this case, I want to send it back to a data store where the data science team will create some dashboards to show to the users when the data is received and have anomalies. And so there can be done a lot of analytics based on the result, right? Showing at what time the anomalies are happening, what is the frequency of anomalies and things like that. So that's what we're going to do. We're going to create another activity here, a data store activity. And here we are going again to select the same data store. We configured the Postgres database. And here on the content, by default, we are just storing the data that comes from the device. But also you can, if you are using a inference activity before that, you can also save onto the data store the enriched data. So that means the results from the inference. So that's what I want to do and connect these two activities together. That's pretty much it. So it's very straightforward. As you guys see, there's no coding. It's just a basic drag and drop of activities, and you are done. And now let's give it a name. So I'll give it a name called infer sound. And then the type, again, I am going to select to deploy this to the edge, to my Raspberry Pi, and then I'll do the deployer tab and air deployer. And with that done, I can say my pipeline, as you guys can see, it becomes part of my set of data flows that I have available. And in this case, I am actually going to deploy this pipeline. So when I click the deploy activity, you guys can see that the request was received successfully. So what is happening behind the scenes is that all this configuration that was created on the user interface is saved and sent to our air deployer that is running. It can be running, in this case, it's running on my Mac, but it can be running on the cloud or wherever you select to run that component. So that component is picking this configuration and converting into a TIBCO Flogo application. The TIBCO Flogo application then is compiled and executable is created for the platform that we selected. In this case, an ARM64 device is the Raspberry Pi. So once that executable is ready, it's containerized and then it's deployed to the device. And that's what just is happening right now. It takes a couple of minutes to complete all those steps, depending. So let's wait a little bit. But the point is that once that is deployed, the data that's coming from the fan will be passed to the model. The model will be called, and then the data will be stored in the database. So I think that should be almost ready. Let's wait a few more seconds. Okay, so I am looking at my other screen and I can see that the model is getting started. I think there was some issue probably that I cannot see.
The curse of the live demo.
Yeah, actually the model is, the process is up and running. So right now the data is flowing through the process and is being saved. So right now, if I stop this share, let me share another screen. I am going to share my, I didn't start it yet. Hold on, let me start my database viewer here quickly. So right now, some data is flowing. Actually, I am seeing. Let me start my Postgres viewer so we can see the data as it's flowing. Just 1 minute. Be patient with me, please. I forgot to start this application. Sometimes it takes a little bit. But I am seeing on my Raspberry Pi screen, and I can see that data is flowing and is working as expected. Okay, so let me share my screen. Where's my database? Can you guys see my screen?
Yes.
Okay, so let me open my database. This is a database actually is running in AWS. We call it Air database here. And here's where the table that we're using to see and view all the data. So there's a huge amount of data that is being saved. So sometimes the queries take a few seconds to come. The query is working. So we will see a few new records that have been saved into the database. Here we can see, for example, we can see today's day, they have been saved here. We can see that this is the device that generated the event. The name of the resource is the microphone. And here's the data that actually was saved. You can see it's an array of, it's a WAV file that has a bunch of numbers. And then on the bottom, we can see that a resource called microphone infer. So that's what was the result of the model. So we save it with the same name of the resource that generated, and we just add the infer. And here, if I click that, we can see the result of the model. It just gives us a prediction that it says 1, so it's a normal reading, and also it gives us like the score of the prediction. That concludes the part of this section. I'll give it back to Atir or Atir.
You're on mute, Atir.
Oh, sorry, I was on mute. Can you see my screen?
Yes.
Yes.
Yeah. So now after Marcelo performed the step of the prediction, we have here a Spotfire dashboard that connects to the AWS database that he created for the output. And basically what we are doing here, we are like reconstructing the input files into these spectrograms. And we also connect to the prediction to basically just display the images into like whether they are like normal or non-normal. So what you are looking here, each spectrogram is one sample. You have the sample number here, and then you have normal. So whenever the model will start detecting abnormal, we should have like another column here to display the abnormal sound files, or like the abnormal predictions as per the model. And this is this dashboard is set to refresh every 30 seconds, but we also can just like manually pull up like new data from the model here. It's simple, but it shows you how can you like see the model performance and the prediction, and then you can also compare like different models if you want to go with that way. So that concludes the part of the visualization and Spotfire implementation. Ahmed, do you have any input thoughts?
Yeah, so this basically concludes the story. This is the consumption layer. In this case, we chose a visual consumption in Spotfire. You know, we left this, you know, back and forth, as you may have noticed. The sharing the screen went back and forth a few times. That was intentional. That was to mimic how this breadth of products and technologies enable connected intelligence that I was, talking about in the beginning. It was the past hour or so was a real case of that, where we started from the problem definition in the real world, collecting the data at the edge, all the way to what we are looking at today. And in the process, Athir and Marcelo literally showed those different personas at the edge and the analytics, and then back to the consumption layer. And as you saw, the majority of the operation was no code. That's also intentional by design. There's obviously some steps in the modeling phase, or when you set up your databases in Project Air, that needs initial setup. But the rest of it, we were basically able to show the whole story in under an hour, and that's the intention, to lower the bar for participation from all of your different personas in your organizations, and bring these projects to fruition. And so before we turn into Q&A, let me share our contact slide. If you prefer to contact us in the future offline. And Kevin, back to you. That's all we had to present.